10.2, regular Markov chains. Recall the Johnson and Northclean example from section 10.1. We had a transition matrix that looked like this. And remember what that meant. It was trying to show you the probabilities of transitioning from one of the dry cleaners to another. So, for example, a person that goes to Johnson one time has a 0.8 probability of going to Johnson the next time. That's what that means. Then we talked about distributions. And we see some distributions, a whole bunch of distributions for two separate examples. So look at the one on the left. The initial distribution says 40% of the people, 40% of the people go to Johnson and 60% of the people go to Northclean. That's the first set of customers, okay? 40% and 60%. So then there's something about this transition matrix, and they use that transition matrix and calculate the first distribution and the second and the third and so on and so on and so on, all the way down to, I stopped at the 14th. Okay, that would be after 14 transitions or 14 batches of clothing. And you can see at the end, it looks like 63.64% and 36.36% for Johnson and for Northclean. But what's weird is you take a different initial distribution. Notice the second problem has a different initial. 75% of the customers went to Johnson and 25% to Northclean. And there's just something about this transition matrix that makes it stabilize to the same exact result. Okay? It's kind of an interesting result. It says, examine the distributions for two separate initial distributions. Discuss the long-term trend. That's what we're getting at with the Markov chain, is we want to know what's going to happen in the future. We're trying to predict the future or discuss the long-term trend. So what does it look like? Well, it looks like 63.64% are going to go to Johnson and 36.36% are going to go to Northclean. So let's say that. I'm going to say in the long run, in the long run, 63% go to Johnson and 36% go to Northclean. And it doesn't matter what they started with. It doesn't matter what the initial distribution was. That's what's going to happen in the long run. Markov chains are good for making long-range predictions. We can make such predictions if the transition matrix is a regular transition matrix. Remember, a transition matrix is made of probabilities, numbers between 0 and 1. A transition matrix is regular if some power of the matrix contains all positive entries. Students kind of have a difficult time with this. A Markov chain is regular if its transition matrix is regular. So what we're going to be looking for to show that it's regular, that's what we have to do in example 2. Determine whether each transition matrix is regular. We have to show that some power of the matrix contains all positive entries. Okay? So the matrix to the second power, to the third power, to the fourth power, to the fifth power, to the 99th power, whatever. Some power contains all positives, then it's regular. So you see these examples in example 2, and you see a lot of zeros. Okay? Zeros are not positive entries. We're looking for positive numbers like 0.75 or 0.25. We want all of the numbers to be positive numbers. So let's go to our matrix calculator. So remember, you can go to my website, Goldadder, and go to the math sites, and then find the one that says matrices. If you want to use your graphing calculator, use your graphing calculator. It's fine. Either way. But let's enter that first matrix as A. Remember, these are probabilities, so these numbers must be between 0 and 1, and the rows are always going to add up to 1. All right, so remember that. Whoops. Didn't mean to do that. So let's just take that matrix A and raise it to the second power and see what happens. Okay, we probably don't need 30 sig figs. Okay, so if you hit A squared and I put 4 sig figs, you notice the result shows exactly what I'm looking for. What was I looking for? All positive numbers. So as soon as we get here, we're done. Okay, we know this matrix was regular because A squared contains all positive entries. So I'm going to call this matrix A right here. And we can write down A squared was 0.5625, 0.3125, 0.125, 0.3, 0.45, 0.25, 0.45, 0.35, and 0.2. Okay, and as soon as we see all of the entries are positive, as soon as we see that, we know A is regular. That's it. That's all it's going to take. So you're probably guessing that the second one is not regular, but let's make sure and show why. So we enter that in. I'm going to put it over here for B. And we'll do B squared. And when you do B squared, you see some zeros. Okay, so let's try B to the third. Still see some zeros. B to the fourth. B to the fifth. Not only are we seeing zeros, but we notice the zeros are always in the same locations. They're always in the same spots. And so that should lead you to a conclusion. It doesn't really conclusively prove that those are always going to be zeros, but I've got a pretty strong suspicion that those zeros are going to stay zeros in those same spots forever and ever and ever, no matter what. Let's try 99. Okay. I've still got those zeros. Okay. There's no getting rid of those zeros. I'm never going to have all positive entries. So, you can write some of the examples. But all of these have zeros. I'm going to put B to the nth power will always have zeros, or will always contain zeros. So B is not regular. And I'm telling you right now, students kind of struggle with this question because they don't know quite what to do. But just do what I just did. Take a couple of powers of your matrix and see if you can get those zeros to disappear. All right. Now I'm not talking about negatives. You don't want negatives because then they're not probabilities anymore. Probabilities have to be between 0 and 1. So when they say all positive entries, they're talking about knocking out the zeros. Okay. That's a good place to stop.